Welcome back, students. In this video, we're going to dive into nomenclature, where we're going to learn how to name alkanes. When we name alkanes, or name any compound in organic chemistry, we have a very particular way of naming. And we want to just start off by talking about what an alkane is. So we've already talked about some functional groups in the past, and now I just want to remind you that for alkanes, you have a formula where you have the number of carbons times 2, and add 2 to that is the number of hydrogens that you have. Right? This is called a saturated compound because it has all single bonds that are possible. Right? It doesn't have any double bonds or rings or anything like this. And this is what we're going to learn how to name first, our alkanes. And when we consider alkanes, we write the carbon first in the structure, and then we write the hydrogen if we're looking at a chemical formula. But as you know from talking about constitutional isomers, you can have one chemical formula that gives rise to a variety of actual compounds. And so what we need is to have names for those compounds. When we name the compounds, we're going to name them for the number of carbon atoms and the location of carbon atoms. We're also going to pull in other ideas as we get more advanced into naming. In general, your name is going to have 2 parts to it. When we first start, it will have the parent, and then it will end with the suffix. So I want to show you on the next page where some of the words and prefixes are going to come from. The parent is determined by how many carbons are in a chain. And the prefix for that parent is going to be listed here in this table. You have 1 carbon atom, the prefix is going to be meth. 2 carbon atoms, the prefix is eth. And notice how meth and eth are kind of new. Prop, I don't know, is prop new to you? It might be. But, not but, for number 4. And then we get to 5 and on, and then these look like Greek prefixes now. Like, we're happy, right? 5 is pent, 6 is hex, and so on. But these first couple kind of throw people off because these are something that you're not used to seeing. So you want to make sure that you have this table memorized. Now at this moment, you don't need to sit down and get a flashcard and start memorizing it, but you should be doing enough practice with nomenclature that this just becomes second nature. So why do we use IUPAC nomenclature? We use IUPAC nomenclature because our desire is to have one name for a particular structure. Now remember, with constitutional isomers, a chemical formula just isn't enough. So if we look at something like C6H, let's do 14, and we start to come up with different structures for this, we can have 1, 2, 3, 4, 5. We can have our carbons be in a straight chain. We can also begin to have branching, and we can keep branching, and we can move the locations of the branches. And all of these have the same chemical formula, but they're different compounds. And these different compounds, they're all special. They have their own physical properties, and they have their own chemical properties, and they need their own name. And our desire is to be able to have one name per compound that all the chemists can agree upon. And with a systematic name, where each letter and each dash and each piece of the name means something, what we can do is, if I give you the name, you can figure out what the formula is. And if I give you the formula, you can figure out what the name is. And when I say formula, I don't mean C6H12, I mean like the actual connectivity of the atoms. So this is why we use IUPAC nomenclature, because IUPAC nomenclature is an international system of naming that has a whole bunch of rules in it. And we're going to dive into the beginnings of those rules. Let's start by naming what are called straight chain alkanes. Straight chain alkanes are just when you have an alkane that's zigzagged, right? Alkanes is all carbon-carbon single bond. Straight chain, even though it's not, straight, it's zigzag to us. The first thing that I want you to do is count your carbons. So I'm going to start with the example on the left. I have 1, 2, 3, 4 carbons. Now I'm going to mentally go back to the chart that we just saw a moment ago and say 4 went with a prefix of bute. So this was bute, and because it's an alkane, because there's only carbon-carbon single bonds, we are going to have an ending of ane, right? So the BUT, the bute, means carbons, 4 carbons in a row. The ane means alkane. So each part of the name is going to be meaningful. Let's do the next one. 1, 2, 3, 4, 5, 6 carbons in a row. So I go back to the chart. 6 is hex. And because I have all carbon single bonds, the suffix is ane. So this is hexane. Naming straight chain alkanes is pretty simple. As long as you know the prefixes. It gets more complex than that when we start putting branches on. Now I want to talk about those branches and some of the rules that apply to those. Before we even really get into branches, I want you to first practice selecting the longest continuous chain of carbon atoms, because that's going to be what we call the parent. And then those branches, those are called substituents. I want you to look at the example on the left and just kind of start from each point and count, how can I get the longest continuous chain of carbon atoms? So what does continuous mean? It means that you're not hopping over something, right? You're counting in order. So I want to do the first one with you, and then I'll give you an opportunity to try the next one. So for this one, I'm just going to start in this upper left-hand corner. So I'm going to call that 1. So 1, 2, 3. And now I can make a choice. If I go down, that's one direction. If I keep going across to the right, that's a different direction. What I see right now is if I keep going across and to the right, I would get 4, 5, and 6. But if I go down, I would get 4, and I'm not going to go to the left because that ends it. Right? 5, 6, 7, 8, and 9. So that's the direction I'm going to go. I'm going to go down and to the right. So I'm going to erase these numbers, and I'm going to highlight my longest continuous carbon chain. So my longest continuous carbon chain was 9 carbons. Why don't you look at this next one and see if you can give that one a try? All right, so for this one, if you were careful, you actually saw 2 chains that would give you 8 carbons. I'm going to highlight one of them here. So that is one way for you to get 8 carbons. Another way to get 8 carbons would be to start on the left and just go straight across. Now for IUPAC, you need a set of rules that we're going to consistently follow. If you happen to have 2 different ways that you can number and get the same number of carbons in your parent chain, what you do is you choose the way that gives you the most branches. So here, 2 directions give you 8 carbons. You choose the direction that gives the most branches. Remember, those branches are called substituents. Now, in order for that to make sense, we probably need to figure out what a substituent is. Here I want to focus on substituents. We're going to put the naming the parent aside for a moment. We're going to look at substituents, and then we're going to bring it all together. If I look at this long chain, I'm going to highlight my parent here. Everything I've highlighted is a carbon that's part of the parent, which means that the pieces that are coming off of that parent chain, those are your substituents or your branches. So here's a branch, here's a branch, and here's a branch. So I have 3 total branches here. Notice how this branch on top contains 2 carbons, 1 and 2. The carbon that it's attached to in the yellow, I'll circle right here, right? Where it's attached, that's not part of the branch, that's part of the parent. So don't count that. This is a 2 carbon branch. Over here, you have a 1 carbon branch. Where I'm circling is where that branch is attached to the parent. That is part of the parent. It's not part of the branch. And then finally over here, 1, 2, 3 carbon branch. And when we name branches, we're naming that again off of the number of carbon atoms in the substituent. So the substituent and branch, right, are the same thing. And if I have a 1 carbon branch, I call that a methyl. So this is methyl. If I have a 2 carbon branch, this is called ethyl. If I have a 3 carbon branch, it's called propyl. Notice how these prefixes, meth, eth, prop, but, pent, hex, hept, oct, non, dec, all of those were the same prefixes that we saw in our earlier table. The difference is because this is a branch, what happens is the ending of this becomes YL. So when it ends in YL, that's how you know that we're talking about a substituent now, or a branch, and we're no longer discussing the parent. Let's look at our first name. This is what an example of a systematic name looks like, and I want to highlight each part of this. The first thing I want to highlight is the parent. The parent is going to be the part that tells you how many carbons are in that continuous section, and it's going to tell you that it's only alkane functionality. So there's no alkenes or alkynes, and don't worry about naming those. We'll name those later on. The substituents are the branches. The branches are here, ethyl, methyl, and propyl. Right? We know that they are branches or substituents because they have that YL ending, and the eth, meth, and prop tell you how many carbon atoms are in those substituents. Finally, the last portion is called the locant. Think of location when you think locant. This is the location on the parent that the substituent shows up. Also take notice of the notation. There are dashes between numbers and letters. Notice how propyldecane, there's no space here. So propyl, no space, immediately begin decane. This is really important, especially if your class uses an online homework system where you really need to make sure that your notation is appropriate. So what we're going to see is no spaces between letters, dashes between numbers and letters, and once you get to an example later on, if you have 2 numbers next to one another, they're separated by a comma. Here's the thing about the systematic names. Every single letter and number and dash is meaningful. The dashes are more notation, but the numbers and the letters are very meaningful. And your instructor, I would say no matter who they are going to expect you to spell this correctly. Now, if you're my student and you know me, you know spelling is not my strongest suit. It is the thing that I probably struggle most with and continually work on. That being said, if I can spell these things, you can spell these things. Because really, it's not so much about, a weird terminology or a weird sound in English. I think that's why I struggle so much, is English is just an unusual language. But every letter is meaningful, right? If you ended this decane, if this A right here became an E, that's a different structure. That's just bananas. So it really is highly important that we spell these things correctly. Now that we've laid the foundation, let's name something. Here are the steps to coming up with a systematic name. Step 1, find the parent chain. So we want to find the longest continuous chain of carbon atoms. And notice how in this one, I'm going to start on the left. I'm going to highlight here as my parent. I get to this carbon and I think, okay, I could go across or I could go down. Well, if I go down, there's more carbon, so I'm going down. And now I could go left or right. And in this case, it doesn't matter which direction you go, right? You get the same molecule no matter what on the same name, so you can just pick a way. So I've found my parent chain. Now what I want to do is I'm going to find my substituents. So here are my substituents. And I'm going to number my parent chain so that my substituents get the lowest set of locants. Remember, locant is location. It's where the substituent is attached to the parent. So I can number two directions. I can either start numbering from 1 over here, or I can start numbering 1 down here. And I actually want to number both and see what we get. So let's do from the left, 1, 2, 3, 4, 5, 6, 7, and 8. So that's my numbering system from the left. And if I number this way, my locants are a 4, a 5, and a 6. Now let's number the other direction. And to make it clear, I'm just going to erase these numbers. If I number this direction, 1, 2, 3, 4, 5, 6, 7, 8. Now let's write our set of locants if we number this direction. Here we have a 3, a 4, and a 5. So the 3, 4, and 5 is smaller. 3 beats 4, 4 beats 5, 5 beats 6. That's easy to tell. If you're ever uncertain, one of the things that the Klein textbook has suggested is add them. You know, a lot of times if you just add them up, you can see, oh, one set is smaller than the other. So I've numbered them in such a way that I get the lowest set of locants, which is the location where the substituent is attached to the parent. And now I want to just remind myself what the substituents are. So here I have a methyl. Here I have an ethyl. And over here, again, I have an ethyl. Now, by the time you've named a bunch of these, you won't have to do and write out all of this work. A lot of this will go on in your brain. But this is your first time, right? So we're going to write down all those steps. And then we're going to put the name together. And when we put the name together, what we do is we list the substituents in alphabetical order. So the ethyl will come before the methyl because E comes before M. Now, notice how you have 2 ethyls. You need to tell the reader where both of those ethyls are. One is at a 3 position and one's at a 4 position. So the way that we're going to write this is 3, 4. And then we need to tell the reader that there's 2 ethyls. So we'll revert back to our general chemistry prefixes of mono, di, tri, and tetra. So at the 3rd position and the 4th position, we have a total of 2 ethyls, so diethyl. Now I'm going to bring in the methyl, and between the L of the ethyl and the locant for the methyl, there's a dash, right? And then another dash. And now I'm going to say methyl. And when I end my methyl with the YL, now I bring in the parent. So this will be octane. So 3,4-diethyl 5-methyl octane is the name for this. So just remember that if you have 2 of the same substituent, you need a locant for each of them. You need to tell the reader there's 2 of them, and you put a comma between the locants. Let's do some practice. I can do the first one again with you, and then I want you to take an opportunity to try the second 2. So for the first one, you find that longest continuous carbon chain, and I want you to give it a try just for a moment, and then compare. So my question is, how many of you stopped here? Because a lot of times students will stop here because that last carbon is going up and they're like, oh, well, that's a substituent. No, it's not. That's part of the chain. Don't let your teacher trick you. We do that all the time. Because remember, sigma bonds can rotate. There's no reason why they can't rotate down. It's just tricking your eyeball, right? We're looking at longest continuous carbon chain. It doesn't matter which direction the last carbon is pointing. We have our longest continuous carbon chain. Now let's number in such a way that gives those substituents, the lowest locants. If I number from this side, I'm going to get the lowest locants. Don't believe me? Then number from the other side as well, and then you'll see. Now I have two 1-carbon locants. Remember, 1 carbon is methyl. So I say at the second and the third position, I have a total of 2 1-carbon substituents by saying dimethyl. And then I finish with the parent. The parent is going to have 5 carbons in it. And so I use pent for 5 carbons and ANE for my suffix. This is the name for the first compound. I want you to give the second two a try, and then we'll come back and we'll compare answers. Welcome back. So I already highlighted my parent chains and I numbered the direction that was going to give me the lowest locants or the lowest set of locants. For the middle structure, I have a 2-carbon branch right here that's showing up at the 4th position. If I would have numbered the other way, then I would have gotten a locant higher than 4, which is why I chose to start at the bottom left. So I have 4-ethyl nonane. The non is saying that there's 9 carbons. The ANE is saying that it is an alkane. For the bottom one, I numbered this direction because it gives me the lowest set of locants overall. And I have 2 methyl groups here and 1 ethyl group. When we put the name together, your E for ethyl gets listed first. So we need 6-ethyl, 2,3, oh my gosh, not 2,3, 3,7 dimethyl. And then this is decane. Usually by this time, students ask me if it's possible to have a chain that's bigger than decane, and the answer is yes. It's just that we usually don't cover that in this level of organic chemistry. Now I want to go into complex substituents. So sometimes substituents can get a little bit, well, complex. And a propyl group can be rearranged in a different way. First, I want to show you my notation here. So R is just saying that this is attached to some bigger chain and that these 3 carbons are my substituent of propyl. If we rearrange the propyl group, what can happen is we can take that final carbon, this one right here, and just kind of put it right there. And if we do so, then there's a branch, and this is called isopropyl. These complex substituents have their own particular names that are really helpful to know so that you don't have to have a name within a name. Because if you don't call it isopropyl, you would have to essentially name the substituent with some other rules that are similar to what we've talked about, but I don't like to do that in my class. I just like to use isopropyl and the other substituent names that I'm going to show you. The butyl group can also be arranged in a couple of other ways. So one way for the butyl group to be arranged is if we take the end carbon, so here are my carbons of the butyl group. Here's the big branch that it's attached to. If I take that final carbon and I just, instead of connecting it here, right, I connect it here, then I have a group like this. And I could also scooch that methyl back one more, and then I can also do this. The first one that I listed here is called isobutyl. The second one that I have listed is called secbutyl. And then the third one is called tertbutyl. At this point, students will ask about that alphabetical order because you know when we take our names and we put the whole darn thing together, what ends up happening is we list the substituents in alphabetical order. But it gets a little tricky right here because the iso is technically part of the name of that substituent, so it counts for alphabetical order, right? Same up here. Whereas the sec and the tert are considered prefixes for the butyl group and don't count for alphabetical order. And that's obnoxious, but it's the way it is. You also, if you are not in my class, you probably just want to check those rules with your teacher to make sure that they agree with that. Let's look at one more set of complex substituents. The pentyl group can also be rearranged to come up with two other complex substituents. Let's look at that rearrangement. What I'm going to do for the pentyl group is move, again, this final carbon to one carbon earlier. This is going to be called isopentyl. Do you notice a pattern yet? That when you take that final carbon and you move it over just one attachment earlier, that's where we get that iso prefix from. Even though it's not actually considered a prefix because it's part of the name and counts for alphabetical order. But you know what I mean. This final structure that I've drawn, this one is called neopentyl. Now, if you had to remember just a couple of these, I would say that the two most important are going to be isopropyl and tert-butyl because they're the most common. So keep those ones at the forefront of your mind and then just be aware that there's some other ones. The final thing I want to talk about with nomenclature is naming alkyl halides. Alkyl halides are compounds that are alkanes that have a halogen group as a substituent. When you name alkyl halides, the nomenclature rules are going to be the same. You're going to find the longest continuous set of carbon atoms, and that's going to be your parent. And then when you start assembling the name and finding what your substituents are, your substituents might be a halogen, and that's fine. The name of the halogen changes a little bit though. So instead of fluorine, you have fluoro. Chlorine becomes chloro. Bromine becomes bromo. Iodine becomes iodo. We're still going to have that same idea of we want a number to get the lowest set of lock-ins. If we go through this example here, let's highlight our longest continuous carbon chain. Don't let that downward pointing carbon fool you. That's part of the longest continuous carbon chain. And then we can start numbering on the left because doing so is going to get us our lowest set of lock-ins. So 1, 2, 3, 4, 5, and 6. When we assemble this name, F for fluorine comes first in front of M for methyl. So we're going to write 2 fluoro 4 methyl hexane. Always be really cautious with how you spell fluorine. If you're spelling flower, you know you have your vowels switched, right? It's fluoro. All right, let's end with a couple of examples. I'm going to give you a moment to fill these in, and then we can compare some answers. All right, now that you're ready to compare, let's talk. For this first one, I actually didn't finish it because you need to know one more rule. And that rule is if you can number 2 different directions and get the same lock-ins, then you use a tiebreaker. And the tiebreaker is the substituent that comes first in the alphabet gets the lower lock-in. Right? Again, this is only if you can number 2 different ways and get the same lock-ins. So there's a priority here, all right? So rule number 1, find your longest continuous carbon chain. Rule number 2, number in order to give the substituents the lowest set of lock-ins. Then comes a sub-rule. If you can number 2 different directions and get the same lock-ins, then you use the alphabet as your tiebreaker. And I comes first in the alphabet before M for methyl. And so this is going to be 2 iodo 4 methyl pentane. Great. So for the next one, now the sub-rule doesn't apply. we have to start numbering on this side because numbering from the left to the right gets us the lowest set of lock-ins. So this is going to be 5-bromo 2,3-dimethyl heptane. All right, the last one. We have one possible parent highlighted. I want to highlight another possible parent now. I'm going to just highlight on top. We have two potential parents. How do you decide? And this is the rule, the tiebreaker for what if I have two parents that give me the same number of carbon atoms, which if I counted correctly, you should get 9 either direction. I'm just going to double count really quick. 1, 2, 3. What you do is when you can number 2 different directions and get the same number of carbons in your parent, you choose the way that gives you the most substituents. Because what you're trying to do when you choose the way that gives you the most substituents is you're trying to break up complex substituents. And that's our goal. So we're going to choose the yellow route. I'm going to go ahead and erase the blue route. And when we choose this direction, now we have to go back and figure out which way to start numbering. So let's take a moment to do that. I'm pretty sure it's going to be this way. 1, 2, 3, 4, 5, 6, 7, 8, and 9. So we're going to number this direction because choosing the other direction would give us a higher set of lock-ins, which I wrote off on the side. Now let's assemble our name. We have 3 methyls now and 1 ethyl. And when we list our substituents, the substituents are listed in alphabetical order. So the ethyl comes first. Now I have 3 methyls, so I have to list a lockant for each of them, 2, 5, and 8. I have to say there's 3 by saying tri. I have to say there's methyl. And then we end with nonane. You did a beautiful job. I'm very excited. I love chemical nomenclature. I love the systems. It's so beautiful. You just have to make sure that you are putting the rules in order. So let's recap them one more time. Find the longest continuous set of carbon atoms. That's your parent. If you can number 2 different directions and get the same number of carbons in your parent, choose the route with the most substituents. Then number in such a way to get the lowest set of lock-ins. If you can number 2 directions and get the same set of lock-ins, then you choose the route where the lowest lock-in goes to the substituent that's first in the alphabet. Let's wrap up. In this video, we did a lot. We looked at the general formula of alkanes. We looked at IUPAC nomenclature. We named everything, including substituents, branched alkanes, complex substituents, and halogens. In another video, we'll come back and we'll keep naming. Thanks so much for your attention. This is Katoni signing out.